various projection formulas that can be used to define to write in stereoisomers. Various projection formulas include the first, the Birchhoff's rule, the Newman rule, the Klein-Spilov rule, the Fisher, the flying wedge conformation, and the zigzag conformation. Okay, now I'll come to each of them one by one. First is the Birchhoff's rule that was first well identified long back in 1859. What he did was that he established the tetrahedral nature of carbon. He established a structure like this, where we have a circle and we have something that looks like a star. Is actually nothing but the conformer of ethane. This is nothing but ethane. How is ethane? We can write. Imagine a carbon in the center of this. There are 3 carbons, 3 hydrogens over here, 3 hydrogens over here, and on the back of this, you can imagine another carbon on the back of this. That is attached to this hydrogen over here, this hydrogen over here, this hydrogen. This looks something like a star. We have this. This actually represents the tetrahedral nature of carbon, where it is attached to 3 different hydrogens. And the back, this triangle on the back, where you have a carbon in the center attached to 3 different hydrogens. This is actually the Birchhoff's rule. Now it is outdated, so we don't use this a lot. And this was first established way to write stereoisomers. Very recent method and a very popular method is a Newman projection. We have already discussed about Newman projection. Just a quick recap of this. This is a Newman projection where we already discussed about this. We view it from the front. Suppose this is something like butane. We view one of the carbons from the front like this, where we have the CH3 projecting up and the CH3 projecting up. This is nothing but, we already discussed, fully eclipsed form of butane. Fully eclipsed form of butane. This actually represents this. This is actually the carbon where it attached to 3 different groups. We know that, and we can also write the various different forms like fully eclipsed form, partially eclipsed form, Gauge form, and the anti form. We have already discussed all this. Similarly, we can correlate this Newman form to the Sawhorse form. This is just a correlation of the Newman form. The Sawhorse form is nothing but we just simplify the structure. Like we simplify this carbon over this carbon is nothing but this carbon. With this carbon attached to this CH3, H and H. Similarly, this is attached to this H and this H. And the carbon at the back that is not visible to the viewer. This carbon is nothing but this carbon. This is attached to this CH3, is this CH3, this H and this H. Clearly you understand this is a correlation of the Sawhorse form. Similarly, you can try the Sawhorse, writing the Sawhorse form of the Gauge form and the partially eclipsed form, maybe the anti form also of N-butane. Maybe it's a part of your homework. We do this. Very important is the Klein-Spilov form. This is not present in any of the books. What it tells that we take a circle, divide the circle. This is nothing but a 30-degree angle. It's a minus 30 degree. Similarly, this is the same. This is a 90 degree. Okay. Now what it divides the circle first into 2 equal halves, top half and the bottom half. This is actually known as, this part is actually known as the spin part. The spin part. This part and the bottom is known as the anti-part. Anti-part. Now this part that is shaded, that I am just shading now, this part is known as the periplanar part. And this part that is unshaded right now, this part and this part, this is known as the Pinan part. So repeating it once more, there are 4 parts. This is the top part is actually that we are representing the spin part, and the bottom is the anti part. The part I have shaded is the periplanar part. The part that is unshaded is the Pinan part. And this we can write is as this now is the negative part and the positive part. Okay. Now how do we correlate this to structures? So what I have taken is that over here is 1,2-dichloroethane. 1,2-dichloroethane. Now we can write it in 2 different conformers. Now according to the Newman, this is the Gauge form and this is the anti form. Now according to this Klein-Spilov, it is taking, what it is telling is that now we know the angle between this is 60 degrees. We already discussed this. Now the carbon that is at the back of this chlorine that we see over here is actually projecting into this Sc part. You can see over here, this chlorine is actually in this part. This chlorine that I am talking over here is actually in this part. So you can write over here, this is Sc12-dichloroethane. This is a different type of nomenclature. The Klein-Spilov, you can write Sc12-dichloroethane because the carbon that we see, this chlorine attached to this carbon is actually projecting into this Sc part. Another example that we can discuss further, anti already discussed. this chlorine that you can see is projecting into this part now. This shaded part now. So this is nothing but AP. This is nothing but this can write as plus SC. This is nothing but AP 1,2 dichlorochlorine. 1,2 dichloroethane. This is very important. Okay. Now we come to the most important part, that is the Fischer projection. Very important. The first major thing about Fischer projection we need to remember is that we have drawn lines like this. We simplify drawing by lines. We have just drawn lines to represent this. Actually, this picture over here, this is a carbon. This is also another carbon over here. This is also another carbon. This carbon attached to COH, OH, and H. This is another carbon attached to COH, OH, and H. This is nothing but tartaric acid. This is nothing but tartaric acid. Both of them is nothing but tartaric acid. Now, just quick recap of what we already studied. This penultimate carbon is having an OH on the left, so this is definitely, we already studied, this is L-tartaric acid, and this OH is having on the right, this penultimate carbon is having on the right, so this is capital D tartaric acid. Capital D tartaric acid. Okay. Now, very important thing about Fischer projection is that this horizontal line that you see over here, this horizontal line is actually projecting towards you. So this is not this, we are drawing it like this, but this is actually nothing but like this. This is actually projecting towards you. These horizontal lines. This is actually this projecting towards you. And this vertical line, this is actually projecting away from you. This is the way you represent it. This is the way you simplify it by drawing straight lines. The horizontal line is projecting towards you, coming away from the ball, and this is actually going inside the ball. This is projecting away from you. This is the way you represent a Fischer projection. So you can write Fischer projection. Now let's assign a nomenclature to this carbon. Let's assign a nomenclature, RMS nomenclature to this carbon. Okay. Now let's assign priorities. As you already know, this will definitely having priority 1. Now among this and this is directly attached to carbon. This is having priority 2. Now this is having a priority 3. So on this carbon, we will having a group like this. So this is something like an S conformer. So we can write it an S. However, what we see over here is that his hydrogen is the lowest priority group. Hydrogen is towards you. The second step is that the hydrogen should be away from you. What does the golden rule state? You have to reverse this. So this will be an R conformer. This is an R conformer. Again, for this point now, for this carbon, again, assign priorities now. This will be 1, this will be 2, and this carbon is 3. So what we have is like this. So we have S. However, again, we have a hydrogen that is facing towards you. So this will be reversed. So this is R. So actually, L-tartaric acid is nothing but 2R, 3R tartaric acid. Tartaric acid. Similarly, try it for D-tartaric acid yourself. This is a part of the number. Try it for D-tartaric acid. So just always remember this hydrogen is towards you, and then try it. Okay. Now Fischer can directly correlate to the flying wedge conformer. What does this flying wedge conformer says? Flying wedge is nothing but correlation of the Fischer. We already have studied that this position is R. This position is R. So just like sawhorse, we draw a line and we draw 3 groups. Arbitrarily we draw 3 groups. Now we don't know actually how to draw this. Just arbitrarily I have drawn this. I have written COH over here. I have made it up. We have to actually make one bold over here. I have written suppose H over here and OH over here. Now we assign configuration to this. Now assigning configurations. How do we assign configurations? This will be priority 1. This will be priority 2. This will be priority 3. And definitely hydrogen will be priority 4. Again, what happens over here? We can understand this will go like this. So this is clockwise direction or an R. However, hydrogen is towards you, so this will reverse this. So what we are getting is getting an S on this carbon. And for this, suppose I arbitrarily written it like one on the plane is COH, coming towards us is OH, and H is coming inside, going inside the plane. So I will give configurations like 1, and this is 2, and this is 3. So we see a clockwise motion. So this is R. So what we get is actually an S and R. It's not matching with this L-tartaric acid. So this is actually not the structure. The correct structure will be something like the correct structure will be, now I redraw this, something, so our configuration at this point was right. So let me change the configuration at this. Change the configuration, I made this one as bold and hydrogen towards the plane. Now I assign configuration is 1 and 2 and 3. So what I get is 1, 2 and 3. So what I get is clockwise rotation, that is R. We already had an R over here. So this matches with this now. So the representation of L-tartaric acid in the flying wedge form is actually this. So your homework lies in representing D-tartaric acid in the flying wedge form. Just try this in D-tartaric acid on the flying wedge form. The last but not the least is definitely the zigzag form. It's very simple, just a correlation of this flying wedge. Just we negate these hydrogens that are into the plane. Just don't write these hydrogens. Just represent this OH. Just we have this bold OH in C over here and have bold OH represented as here. Just write this 2 OH and just write this COH in the zigzag manner. Zigzag definitely tells us this zigzag manner. And just project this OH over here and project this OH. Negate. Don't write the hydrogens. Just this is the representation of the L-tartaric acid. So the homework would also be to write D-tartaric acid in the zigzag form. So your homework will be to, I just have shown for L-tartaric acid the Fischer form, the flying wedge form, the zigzag form. Similarly for D-tartaric acid, the Fischer is shown. You have to write the flying wedge and the zigzag form. That concludes my session regarding the projection formula and the various types of D and L and the various types of isomerism. So thank you. I hope this was helpful.